Hello, and welcome to Engineering Dynamics. My name is Joe Graber, and I'm going to be your instructor for this class. This first video is really just to give you an orientation so you understand what engineering dynamics is and where it fits into the rest of your education. So let's go ahead and get started. Engineering dynamics is part of the engineering mechanics sequence, the fundamentals of engineering. There are three branches to this sequence: rigid body mechanics, non-rigid body mechanics, and fluid mechanics. Within each of these categories, you can break them out. Okay, rigid body mechanics can be separated out into statics, which you're all familiar with because you had to take that class in order to get into this one, and dynamics. It's important that we remember that these are both part of rigid body mechanics. The reason this is important is because there's this large underlying assumption in rigid body mechanics, and that is that there is no deformation. Okay, is that a good assumption? Well, in some cases, yes. We can find out a lot of good information about a body, but we have to remember that assumption because in reality, everything deforms. You can be standing on a cement sidewalk and your body weight is deforming the sidewalk. Not very much, and in that case, rigid body mechanics would be a good estimation. However, there is some deformation going on, so we always have to remember those underlying assumptions. If you're using something that deforms very easily like rubber, or even more so like fluids, then it's probably not a very good assumption. The other branch of engineering mechanics is non-rigid body mechanics. Non-rigid body mechanics, you'll be taking another class in that, most likely, which is Mechanics of Materials, or Engineering 225 here at Everett Community College. In that class, we learn how deformation affects our calculations. And then, of course, there's fluid mechanics. Fluids are either liquids or gases, something that easily deforms under a shear force. And you're going to be taking a class in fluids your junior level. For many of you, that will be after you leave Everett Community College. At WSU, it's ME 303. At UW, it's ME 333. So to give you an idea, that's how it fits into the mechanics sequence. Now let's dig into what dynamics is. So I want to go through a quick course outline of dynamics and what we'll be learning about. Dynamics can be broken up into two broad categories. First one is kinematics. Kinematics is how things move: position, velocity, acceleration. Okay, how I like to describe this is if you're looking at a police officer on the side of the road with a radar gun. Okay, the police officer is using that gun to figure out how fast people are going. So he or she sees a Prius going by, pulls the trigger, Prius is going 65. And then they see a Corvette going by, pull the trigger, it's also going 65. Which one has more horsepower? That has nothing to do with kinematics. We don't care which one has a larger force applied to the wheels. We just care about how fast is it currently going. In kinematics, we're looking at what is its position, what is its velocity, and what is its acceleration, and not how it got there or why it's moving. Okay? Kinetics is the why. Why is that Prius going 65, or why is that Corvette going 65? Well, there was a force on its tires which accelerated it forward. Notice the force comes into play in kinetics. This is why things move, and of course we're going to use Newton's second law, F equals ma, is really the basis of that. Each one of these categories can be broken down further. In kinematics, we're going to start off with a particle assumption. We're going to start off in particle kinematics. What we're really doing here is we're doing scaffolding. We're learning this, we're using some large assumptions to start off with to learn how the math works, and then we'll add more reality as we get further forward. So in particle kinematics, the first word particle, we are making a particle assumption. What does that mean? It means that whatever we're looking at has a mass, but no shape or size. Okay? So you can think of it as we're just paying attention to the center of gravity of an object. So like a rocket shooting off to Mars. We're just going to pay attention to how the center of mass of that rocket moves. We're not going to pay attention to the shape of the rocket. That can be a good assumption in a lot of situations. If rotation is not a big part of its movement, then a particle assumption can be used. So that brings up another point of our particle assumption. In particle assumption, there is no rotation, right? If we're just assuming that all object is just a particle in space, we don't care if that particle is spinning or not. It's infinitesimally small. So we don't take rotation into account, and that's really where this assumption helps us learn translation, which is an object's motion, without considering rotation. After we learn about that, we take off the training wheels and we go to rigid body kinematics, which is a little bit more realistic, where we do take in the shape of the object and the rotation of that object. So we start off, we're going to go through kinematics. We're going to start with particle kinematics. In the textbook we're using, this is chapters 2 and 3. So this is chapter 2 and 3. And then we move on to rigid body kinematics, which is going to be chapter 4. Okay, from there we move on to kinetics. Now kinetics can be broken up into several different categories as well. First, we're going to do the same thing we did in kinematics. We're going to start with a particle assumption. In kinetics, our particle assumption is going to be chapter 5. Then we move on to rigid body. We take away the training wheels. We take away that assumption that everything has no shape or rotation, and we move to rigid body kinetics, which for us is going to be chapter 6. Okay. After we've learned all of that, we've learned kinematics and kinetics using our base kinematic equations and F equals ma as a starter. Then we move on to some other strategies in kinetics. The first strategy is impulse and momentum. We can use F equals ma and we can change it around and use some calculus to get an equation for impulse and momentum. For us, this is going to be chapters 9 and 10. And then work and energy. Work and energy is something you've probably reviewed in physics. And we're just going to go back over that and bring in rigid body, make sure that we understand 3D motion with work and energy. And this would be chapters 7 and 8. So you can see we're going slightly out of order from what the textbook does, and we're swapping these two subjects towards the end. Hopefully that gives you an idea. Oh, one more thing I wanted to mention is you have all been through statics. And in statics, you did a lot of free body diagrams. And in those free body diagrams, you were looking at forces, right? And because you're working at forces, really, kinetics is going to feel more like statics. But we're going to start off with kinematics. Kinematics is going to kind of feel more like physics, where you did position, velocity, and acceleration. You probably learned constant acceleration equations. We're going to be going through all of that and then adding to it so we can get some real-world solutions with kinematics. So we start off with that. That's probably roughly half the class. And then we jump into kinetics, which is going to feel a little bit more like statics, where we go back to free body diagrams and such. Hopefully that gave you an overview of what this class will be about. Please move on to the next video and let me know if you have any questions. Thank you.